I want you to try a mental exercise with me for a second. It might sound a bit strange, but go with it.
Okay.
Clear your mind. Now, I want you to picture the number e, 2.718, the base of natural logarithms.
Okay. I'm picturing a calculator screen. Or maybe a vague sense of panic from high school calculus class.
Right. It's usually just a symbol, a squiggle on a page.
Oh.
Now, picture pi, 3.14159.
Again, just a Greek letter, maybe a circle if I'm feeling geometric.
Exactly. That is how most of us interact with math. It's cold, it's abstract, and it's usually black and white text.
Mm-hmm.
But what if I told you that in the stack of research we're diving into today, E isn't just a number? What if I told you E is red?
And that pi, or specifically the imaginary version of it, is violet.
And what if these aren't just, aesthetic choices? What if painting these numbers with specific colors is actually a tool, a piece of semantic compression that lets us see glitches in the fabric of reality?
It sounds like we're veering into sci-fi or maybe even psychedelics, but we aren't.
Not at all.
We are looking at a really rigorous stack of materials today.
Right.
We have a theoretical framework called CCT navigation. We have Python code designed to hunt for errors and constants. And we even have a white paper for a proposed European Space Agency mission.
The Bit Depth Observatory.
That's the one.
It is a wild ride. We are going from coloring books to the event horizons of black holes. So welcome to the deep dive. We've got a lot to unpack.
We do. And I think to understand the heavy stuff, the are we living in a simulation stuff, we have to start with the colors. We have to understand the CCT navigation.
Complex color topology. It sounds incredibly technical, but the source material actually frames it as an accessibility tool.
Right. The sources make a very important distinction right out of the gate. They aren't doing metaphysics.
Right.
They aren't asking, does the number 5 have a soul, or is math spiritually blue? They are focused on utility.
Utility.
Exactly. They argue that the human brain is terrible at processing raw, complex numbers. We just hit an intelligence threshold. We get stuck trying to visualize a number that has both a real part and an imaginary part. It's like trying to imagine a new primary color.
But our brains are excellent at processing color and spatial navigation.
Yeah.
We evolved to find ripe fruit in a green jungle.
Precisely. So the goal is semantic compression.
I love that term. It's like zipping a massive file so your brain can download it instantly.
If you can map complex math onto a color wheel, you don't have to calculate the trajectory, you can just see it. You bypass the prefrontal cortex and go straight to the visual cortex.
Okay, so let's build this map for the listener.
Yeah.
Because if we don't get the map right, the rest of this deep dive won't make sense. I haven't touched a complex plane since college. That's the graph with the real numbers on the horizontal axis and the imaginary numbers on the vertical, right?
Correct. Imagine a standard graph. Now, the system they propose uses the HSV color model hue, saturation, and value, and it's surprisingly intuitive. First, you have hue,
The color itself.
the actual color, red, green, blue. In the system, hue maps to the angle.
The angle.
Think of the complex plane. It's circular. You go around the origin. That's 360 degrees.
Okay.
The color wheel is also circular, 360 degrees. It's a perfect topological match. So in this specific mapping, 0 degrees is red.
Okay, 0 degrees pointing right is red.
90 degrees pointing up is green. 180 degrees pointing left is cyan, and so on. It just wraps all the way around.
Does that make sense? A circle is a circle.
Yeah.
What about brightness?
That's the value. It maps to the magnitude or how far you are from the center of the graph. If you are right at the center at 0, it's transparent. As you move outward, the color gets brighter and more intense.
And saturation.
That's the deep cut. Saturation maps to purity or algorithmic randomness. But for our purposes today, just think of it as the intensity or purity of the signal.
So if I'm a mathematician using this system, I'm not just scratching symbols on paper. I'm essentially, walking through a color space.
You are. The source describes it as walking a path. Let's take a simple function to visualize this. Z of t equals e to the it.
You're already losing me with the notation.
Hold on. In traditional math, you'd be calculating vectors. But in this color framework, imagine you are standing in a white room. As time, or t, starts ticking, you see a color wheel start to rotate.
Okay.
The brightness stays exactly the same because the magnitude isn't changing, but the hue shifts.
So I'm just watching the color cycle.
At time 0, you're at white. As you move to pi over 4, the room turns yellow. By pi over 2, it's green. And when you get to pi, you hit black.
You're painting a trajectory.
Precisely. And this visualization tool is what allows us to tackle what is arguably the most famous and most confusing equation in history, Euler's identity.
P to the I pi plus 1 equals 0.
The most beautiful equation.
I've always been told it's beautiful, but honestly, it looks like magic. You take E, which is about growth, raise it to the power of an imaginary number times pi, add 1, and somehow it all vanishes into 0. It feels like a trick.
It does feel like a trick algebraically. It feels like shuffling a deck of cards and having them disappear. But let's look at it through the lens of this color theory. The sources break it down into a story of mixing paint.
Okay, walk me through it. Let's decode this magic trick.
Start with E, 2.718. In our map, E is a positive real number. It sits on the horizontal axis. That means it is red.
Red.
And red represents pure growth. It's warm, expansive, pushing outward.
Okay, I have a bucket of red paint. That's my starting point.
Now look at the exponent, I pi. The I represents the imaginary axis. In our color wheel, that direction is violet.
Wow.
Violet represents pure rotation. It's an orthogonal force. It doesn't want to grow, it wants to spin.
So I have red for growth and violet for rotation.
And Euler's equation tells you to apply that rotation to that growth. You are rotating the red vector by the violet angle. And if you rotate red by 180 degrees, where do you land on the color wheel?
Opposite of red in this system.
In this specific mapping, because of how the magnitude works, you land at black. Black represents -1.
Red rotated by violet becomes black.
And the final step of the equation is +1. In our light-based color map, +1 is white. So the equation is literally saying, take your black result, -1, and mix it with white, +1.
And if you mix black and white light, well, they cancel out.
They become transparent, 0.
Growth plus rotation equals cancellation.
Boom! You just derived Euler's identity without writing a single number. You visualized it.
That is shockingly intuitive. It turns a rigorous proof into something you can almost feel. But, and here's the big but, we aren't just here to talk about a cool way to teach calculus. This deep dive isn't about education. It's about reality itself.
No. This is where the deep dive takes a sharp turn. The sources argue that this color mapping isn't just a fun visualization tool, it is a collapse operator for theory.
A collapse operator? That sounds ominous. What does that mean?
Meaning that if math has a structure, we can visualize this cleanly, smooth gradients, perfect transitions from red to black, then we can also look for flaws in that structure. We can look for artifacts.
Artifacts. Like in a JPEG image when you zoom in too far.
Exactly. When you zoom in on a photo, you see the blocks, you see the pixels, you see the limit of the resolution. The experts in these documents are asking, does the universe have pixels?
This is the simulation hypothesis. But usually when people talk about living in a simulation, it's a philosophy debate. It's the Matrix or a dorm room conversation at 3 a.m. These sources seem to treat it differently.
They treat it as a problem of metrology.
Measurement.
They don't care about the philosophy. They care about the cosmic bit depth.
Explain that term, bit depth.
If the universe is a simulation running on a computer, even a computer the size of a galaxy, it must be finite. No computer has infinite memory.
Right.
Therefore, it cannot handle infinite precision. Real numbers, like pi, go on forever. But a computer can't go on forever. It has to cut the number off. It has to round it.
And if it rounds it?
It leaves a fingerprint,
Yeah.
a truncation artifact.
So if we look closely enough at the math that underpins reality, we should see the jagged edges where the computer gave up.
That's the theory. If the resolution is finite, the gradients of color we talked about earlier, that slide from red to black, can't be perfectly smooth. At the microscopic level, they have to step.
So how do we find the steps? The source material lays out 4 specific modules experiments designed to find those edges. Let's start with the software side. Module 1. This isn't a telescope, it's a Python script.
It is. Module 1 is a resonance peak detector. The researchers propose scanning the digits of fundamental constants, mostly pi, but others too, out to massive depths. We're talking 10 to the power of 14 digits.
100 trillion digits. And what exactly is the script looking for? I thought pi was supposed to be random.
Theoretically, yes. The digits of pi should follow a normal distribution, but this code calculates something called kurtosis.
Kurtosis. Sounds like a medical condition.
It's a statistical term. It measures the tailedness of a distribution. Basically, it looks for outliers. It looks for patterns where there should be chaos.
So if the computer simulating our universe has a limit, say, it can only hold 500 digits of precision, what happens at digit 501?
It has to fake it. It has to use a pseudo-random number generator, a PRNG, to fill in the rest.
And pseudo-random isn't the same as real random.
No. Real random has no pattern. Pseudorandom is an algorithm. And Module 2 in the source material proves this with a fascinating synthetic example. It shows us exactly what a glitch would look like.
Yeah.
Imagine you're reading a sequence of numbers, 3, 1, 4, 1, 5, totally random.
Right.
Then suddenly, at depth 500, the texture changes. You get a sequence, 7, 2, 8, 4, 6, and then 10 digits later, that exact sequence repeats. 7, 2, 8, 4, 6.
It loops.
It loops. That periodicity is the signature of a specific algorithm called the Mersenne twister. It's the standard random number generator used in Python, Excel, you name it.
That gives me chills. So they are saying if we scan pi out to 1 trillion digits and suddenly we see a Mersenne twister pattern.
Then we know with mathematical certainty that pi is being generated by a computer with a hard limit on precision. We would have found the pixel grid of the universe.
It's terrifyingly specific. It's not maybe the universe is fake. It's run this code and see if the sky is a painted backdrop.
And the scary part, the source mentions that we don't even need to find a perfect loop. Just finding a non-Gaussian pale, a statistical lumpiness, would prove the universe has a finite bit depth.
Wow.
It would prove that the numbers aren't real in the infinite sense, they are rendered.
But scanning digits on a hard drive is one thing. That feels abstract. Module 3 takes this concept into the real world, into the heaviest objects in the universe.
Black holes, the ultimate stress test for physics.
We've talked about black holes before. General relativity says the event horizon, the point of no return, should be smooth. That's like a waterfall. Once you go over, you're gone. Nothing comes back.
Right. In a continuous analog universe, the horizon is a perfect smooth edge. But if space-time has a finite bit depth, if it is pixelated,
Then the edge can't be smooth. It has to be stepped, like a staircase.
Yeah.
Or a low-resolution image in Minecraft.
exactly. They call this the bit depth saturation boundary. And here is the physics implication. If you throw a gravitational wave at a smooth horizon, it falls in. But if you throw it at a stepped horizon,
It would bounce.
it would reflect. It creates an echo.
An echo from the edge of a black hole.
The source provides a specific formula for this. The echo delay, delta t, depends directly on the simulation resolution, NSIM. If we can hear that echo, we can calculate the resolution.
Go ahead, hear it.
Not yet. The source cites the LIGO 04 constraints dated to 2026. They haven't detected echoes greater than 0.1 seconds.
Is that a blow to the theory?
Not necessarily, it just sets a lower bound. It implies that the simulation resolution must be greater than 63 bits.
63 bits, wait. My laptop runs on 64-bit architecture. The Nintendo 64 was, well, 64 bits. Are you saying the universe might have the same processing depth as a video game console?
Well, that's the lower limit. It's likely much higher. But the fact that we are even discussing the resolution of reality in terms of bits is mind-blowing.
It is.
It puts the universe in the same category as a consumer electronic device.
It certainly implies we aren't running on an infinite supercomputer. We're running on something with constraints. But 63 bits is just the floor. If the pixels are smaller than that, our current detectors, LEGO and the like, can't see them.
Which brings us to Module 4. If our glasses aren't good enough, we need to build better ones.
The Bit Depth Observatory, BDO. This sounds like the title of a Greg Egan novel or a sci-fi blockbuster.
It really does. But this is a concrete proposal. The ESA white paper described in the source targets a launch in 2032.
Okay, break down the mission profile. What are we sending up there?
3 spacecraft. They fly in a formation, trailing the Earth in its orbit around the Sun. They're equipped with 4-meter UV optical telescopes. But the secret sauce isn't the glass, it's the onboard optical frequency combs.
Frequency combs. I've heard that term in relation to atomic clocks.
That's exactly what they are. Think of them as the most precise rulers ever created, but for time and light. They allow for absolute wavelength calibration.
And what are they pointing these super rulers at?
Quasars. Ancient, incredibly bright galactic cores at the edge of the observable universe. But they aren't just taking pretty pictures, they are measuring a specific number. The fine structure constant, or alpha.
The fine structure constant. That's the number that defined how strong the electromagnetic force is. It's the number that holds atoms together. It's supposed to be constant, hence the name.
Supposed to be is the key phrase. This mission asks a dangerous question. Does the resolution of the universe change over time?
Wait, you mean, does the simulation get an upgrade?
Think about a video game. As you get closer to an object, the level of detail increases. High-res textures load in.
Right.
Or think about the history of computing. Games in the 1980s were 8-bit. Today they are 64-bit.
So they are looking back in time at these ancient quasars to see if the universe used to be 8-bit.
Exactly. They are checking if n of z, the resolution at a given redshift, is static or dynamic. If it's static, the rules were set at the Big Bang and never changed.
But if it's dynamic,
If the resolution upgrades over time, that implies an active administrator,
someone or something allocating more RAM to the system as it grows.
or improving the build. And the sources actually calculate the stakes of this mission using Bayesian probability.
I saw this in the notes. This is where the math gets existential.
It does. Currently, based on our knowledge in 2026, they calculate the probability of the simulation hypothesis at roughly 17%.
1 in 6. Russian roulette odds. Not negligible, but you can sleep at night.
But if the Bit Depth Observatory launches in 2032 and finds that the resolution scales with time, if they find that signature, the probability jumps.
Jumps to what?
96%.
96%.
Yeah.
That's basically certainty. That's game over, thanks for playing.
It would be the single most transformative discovery in human history. It transforms the simulation hypothesis from a what-if into observational cosmology. It wouldn't just be a theory anymore. We would know the specs of the machine we live in.
It's funny. We started this conversation talking about colors, about painting E red and pi violet, and now we're talking about finding the admin of the universe.
It connects, though. The source ties it all back together with the color identity theorem.
Remind us what that is?
It's the idea that the path from red to black, from E to -1, isn't just abstract math. It's a measurable topological path. If the universe is a simulation, that path is the code.
And if you zoom in on that path,
You might see the jagged steps. The color mapping gives us the intuition to spot the artifacts. It tells us what a glitch looks like.
if the transition from red to black isn't perfectly smooth, if it stutters, that's the pixel.
Exactly. The source argues that we don't need to philosophize about reality, we just need to measure it. Nature will reveal whether it is finite or infinite.
So what's the verdict? The expert in the source material. What's their final stance? Are they a believer?
Their stance is fascinatingly pragmatic. They say the simulation hypothesis is no longer about, is this real? It is about, what is the resolution? It's a shift from ontology to metrology. We stop asking if and start measuring how much.
And they aren't waiting for 2032.
No. The source mentions a next 72 hours plan. They are running that resonance detector on 1 billion digits of pi immediately. And they are drafting that abstract for the ESA. This is active science.
It makes you look at the world a little differently, doesn't it? You look at a sunset, all those gradients of red and violet, and you have to wonder, is that gradient perfectly smooth? Or if I look close enough, would I see the steps?
It raises the ultimate question. If we find the steps, if we find the pixel grid, do we try to hack the system?
Or do we just sit back and appreciate the graphics?
That might be the safer option.
I want to leave the listener with one thought from the source material that really stuck with me. It's about that color identity theorem again. If we are in a simulation, then math is the source code. And maybe, just maybe, by painting that code with color, we've found a way to see the developer's handwriting.
Or at least their compression algorithm.
Exactly. Thanks for listening to this deep dive into the color of math and the resolution of reality. Go check the show notes for the Python code if you want to hunt for glitches yourself. Just be careful what you find.
You might not be able to unsee it.
See you next time.